Hello everyone. My name is Anurag Kumar, and I'm from Team Digital Guardians for the assignment FIT3183 unit. So we have been able to build our deepfake detection project. I'm excited to present it. So here's the first part for our challenges that we face. So as we know, deepfakes are a serious threat to our digital world. So as AI gets better at creating fake content, it becomes harder to tell what's real and what's not. And this matters from everything to news authenticity to personal privacy. Our goal was an ambitious one, which is to build a detection system that's not just accurate but also explainable. We want to create something that doesn't just say this is fake. We want to show why it thinks that this is fake, which is important for trust and real world deployment. So for our approach, we went with a dataset that contains 140,000 images that are real and fake faces. For our architecture, we chose EfficientNet B4 and B7, which are well-known models for being powerful and efficient. And we use transfer learning, where we use ImageNet pre-training and fine-tuning on our deepfake data. And what makes our project special is that we didn't just stop at getting high accuracy. We also wanted to implement Grad-CAM for interpretability and ensemble using model combination of B4 and B7 for robustness. So coming to the results that we were able to achieve, for B4, we were able to get a 99.91 accuracy and B7 a 99.89% accuracy. One thing to note is that the B7 result was based on the 5 epochs that it was given, while B4 had a 10 epochs for preparing. And the best part is that our ensemble result, which is a combination of B4 and B7, we were able to achieve a 99.98% accuracy, meaning that out of the 10,000 images, there'd be only two that is wrong. So first thing to note over here is that the test data that we use is from the same distribution as our training set. So cross data set validation would be a valuable next step to assess for generalization across different deepfake generation methods. So, yeah, that's one thing to know. So for better understanding, the results that we achieve are all over here. For B4, this is what we were able to achieve. So yeah, as you can see, B4, the accuracy that we achieved were varying from the 10 epochs that we had. But yeah, as a rough estimate, this is what we were able to get in on average. And then for B7, it's the same thing, 99.89. And for the ensemble is all the way at the end over here. Yeah, this is what we got. This is what we got, 99.98. So now coming to the Grad-CAM visualization, the reason why we wanted to apply this is to show how our model makes the decisions. And yeah, this is where Grad-CAM comes. So to show more easily, these are the results that a Grad-CAM was able to produce. It's a visualization technique that shows us exactly what the model is looking at. So as you can see, the heat maps over here. For the real images, the model naturally examines the facial features, the eyes, nose, and the overall structure. The attention is distributed and it seems natural. But for fake images, like the one over here at the bottom, or these two images at the bottom, you can see that the heat map has a focused area where the model concentrates heavily on these, like certain specific regions. And this is where we find the GAN artifacts at here to show that these images are fake. And as they act as telltale signs that generative AI model leave these things behind. So which is a big finding for us as it helps improve our model that they didn't just memorize pattern. It actually learned meaningful features that distinguish real from fake. So this kind of interpretability is critical for deployment in real world application where we need to trust and understand the AI decisions that are made. So now coming to our ensemble method. So the reason why we wanted to make this model is to see how far we can actually go in making our model accurate. And yeah, that's why we came up with the ensemble method to see how far we can go with accuracy. So yeah, we went from a 99.89 average to 99.98%. Is a rough 0.10% improvement. And this does have a big impact because at this point, the accuracy is already really high. So even a 0.1% is a big achievement, as we were able to reduce 82% of errors that would occur from our either B4 or the B7 model, which is basically that, let's say if it's 99.89%, the 11 failing images are now reduced to 2. Means those out of the 11 failing, 9 are now passing, while only 2 images are failing. It's basically that. So yeah, here are our key achievements. So to summarize, we were able to get near perfect accuracy. Then next thing is interpretable AI, where Grad-CAM proves meaningful learning, as I showed previously, uh, from the visualization that we're able to generate. And for the third part is robust ensembler. We showed how combining model can dramatically reduce errors by 82%. And for last, complete pipeline, we will build a full system from data processing to deployment that's ready for further validation and testing. Now, for any impacts and future direction that we can go with this is in the real world, this technology can protect digital media integrity and combat misinformation and build trust in AI systems. So this helps enable responsible AI deployment where explainability matters. And if we look forward, we see several exciting directions. First and most important, cross dataset validation. We need to test our model in external benchmarks like for face forensics and CelebDF to understand how well it generalizes to different types of deepfakes and the generation methods. So this is crucial for real-world deployment. And beyond that, we'd extend to video detection for real-time application or assess robustness to real-world perturbations like compression and blur, and possibly potentially deploy this as a web service. So yeah, the foundation looks solid and it's ready for future work. And that's all for my presentation. If you like it, you could like and subscribe or maybe even share with anyone that you know. Thanks.